Good morning. Basically, everyone's here today to hear computational intelligence in Earth and space systems. If you're not for that session, please leave. But, okay. First speaker we have today is Mike Friedel. And Mike is going to talk on applications of soft computing in mining undiscovered global porphyry copper deposits. Mike, please.
Number 2. Okay, good morning. Thank you, Mr. Chairman, for the opportunity to share some of my experiences with soft computing and hybrid modeling with applications to undiscovered global copper porphyry resource assessments. So by way of background, I'd like to introduce this concept as something that the USGS has been doing for perhaps 20 or more years. And at the present moment, we are concluding a global resource assessment, and we're going to be beginning in 2013 a national mineral assessment for all of the U.S. on various strategic minerals. So at this point, the USGS is actually in a process of reviewing what's called the so-called three-part assessment process. In this diagram here, you can see on the left, there's 3 boxes that introduce 3 steps. These are the 3 primary steps of the resource assessment process as described by Singer and others. On the left, it begins with the mineral resource map. Then there's an estimated number of undiscovered mineral deposits and grade and tonnage models. And this information is combined and it's introduced into a Monte Carlo framework, and we end up with what's called a quantitative assessment, which gives us some probable estimates of undiscovered resources. There's also a second portion to this under step 5 here that is called the economic resource assessment or analysis. At this present time, though, the USGS has not been pursuing this because there's a series of empirical equations that are outdated. So as a background to this, I'd like to present 3 quotes. The first quote really speaks to the idea that we have a particular paradigm based on where the USGS was at over the last 20 years. And that leads us to the point of today, as was described in the previous session, that we basically have a lot of data. We're almost drowning in the information, but we have a lack of knowledge. That is the information that's locked up in these measurements. So how is it that we're able to take any information out of those measurements? Well, one application that I've been working on for the past couple of years has to do with computational intelligence. And in this area, I've been working with soft computing as well as hybrid modeling. And in soft computing, there's basically a collection of techniques under the heading of machine learning techniques. There has been one paper by Singer and Kuda in '96 that worked with an artificial neural network that's called a feed-forward artificial neural network. And more recently, I've been working with a self-organizing map approach. The difference between these two is one is supervised, and the self-organizing map has the advantage of being unsupervised competitive learning algorithm. It has a distinct advantage in that there's no a priori structure placed on the modeling. So one of the things that this self-organizing map, or the SOM, is good at is data mining, looking at relationships. It also can be used as a classifier. It can be used to impute, if there's sufficient information in the multivariate density function, to impute missing values, and also for prediction or estimation. One of the things that I found that's useful that I'll give an example for is using the soft computing up front and then taking that information and coupling it with techniques that are more traditional, either empirical or numerical, in what's called a hybrid modeling approach. So with regards to mineral resource maps, step 1 of the process, Dr. Canara will talk about approach for defining tracks. These are permissive tracks from undiscovered mineral resources. And Dr. Iwashita will also talk about applications, while not directly related, or well, not directly mineral resources, they will be related to this topic in terms of defining spatial correlation. And the spatial correlation is important for part of the modeling process in terms of looking at relationships, the correlation among tracks when people are aggregating across the world. So in step 2, some preliminary work that I've been working on here has to do with estimating the number of deposits. On the left is some data that Singer published in 2005, and it has 3 different porphyry types, 3 different copper deposit types. One is a porphyry copper, one is massive sulfide, and then a potiform chromite deposit. But essentially that data went into the SOM and classified it using a neural net, a k-means clustering, and use a Davis-Boydin for looking for interesting merges in the system. And then we have what's called a classifier. And from the classifier, you take data that in this case is a split validation, so these data weren't used in the training set, but then are used to, the classifier is then used to actually estimate values. And on the right side, you can see that because the process, the underlying approach is actually stochastic. In this case, I can run this a number of different times and compute medians and also the average, or any statistic for that matter. And we can see on the right the estimated versus the observed data and deposit types are approximately 1-to-1, demonstrating that at least the SOM is relatively unbiased. Now, it's a beginning. Step 3, let's consider the grade and tonnage models. In this case, the characteristics of the grade and tonnage models themselves are that the primary grade is the copper, and then there can be secondary grades as well, which could be one or more of the others, the molybdenum, gold, and silver. Each of these models themselves are limited to some data from across the globe that can be as little as 15 deposits or as many as 420. The variables themselves, because in some deposits the gold or the silver, these secondary commodities, don't show up, there's different data lengths, which makes it a challenge to actually look at statistics among the different data. Certainly the traditional statistics will not work. And also there's some zero values in looking at these data sets. Rather than having missing values, they put zeros in these models. And the zeros really could be a number of different things, including the fact that there was a limit of detection. It could have been a methods change, could have been that there was no data, or it could also have been some economic constraint. So in some of the challenges here that I'll address are the statistics, looking at uncertainty in the data set, and also the structure. Are we looking at apples and oranges? And these sorts of things can be introduced in the quantitative resource assessment. So on the left, this is a component planes plot. We're looking at the circle is the tons in copper, and to the right, if we look at a cross plot between these two component planes, you can see that there's some data, and each of these dots, the scale is scaled relative to the number of information, and the colors represent different deposits from different places in the world. You can see a general trend there, a decreasing trend, and also there's a correlation matrix to the bottom. So right away we can see that we can devise some statistics and look at evaluate some of the things like the correlation. In this case, is Spearman Rho, just a non-parametric correlation because it's nonlinear, but it's monotonically decreasing. So taking the correlation information, fitting distributions to the different, in this case, molybdenum and tonnage, and then running a stochastic simulation, we can generate 2,500 trials and then look at results in terms of the uncertainty. So now we have a way to look at the data set with regards to addressing uncertainty in our limited sample from across the globe. Also, what pops out here is some outliers. So we're looking at molybdenum as a function of tonnage. Next, let's address the zeros. These zeros in the data sets themselves. And kind of as a backdrop, the USGS includes those zeros and has been modeling them. So in the end of the day, when they come up with a quantitative resource number in terms of probabilistic approach, we have these numbers, but we have this binary set of information. So we also have zeros and we have a distribution, which is hard to fit. In other words, the results could be suspect. But in general here, if we look at the upper panel from the self-organizing map, I have done one realization, and we can see that the observed and simulated structure is similar. There's no zeros, so there's no need to do any imputation of the results. But because they have a similar structure, the zeros themselves span over 4 orders of magnitude in terms of tonnage, and the zeros are not zeros. The zeros are real values, and in this case, the SOM is able to identify the approximate magnitude of those values. In the lower panel, this is a panel that shows molybdenum, and also in this case it's molybdenum as a function of tonnage, and we can see that there was a lot of zeros. There were data that we're able to impute, and again they do follow the same structure of the rest of the data set, and so these data are real, they're not zeros. And so we have a way to actually address that and build a model that's slightly better without zeros. Now, if we contemplate the nature of the data sets in terms of their homogeneity, one thing we don't want to use is we don't want to build a model based on apples and oranges. In this case, this population, when we're looking at copper versus tons, has a homogeneous population with some variance. On the right, we see the deposit names, and you can identify the deposits in the world that are associated with the data on the left, in the left panel. Now, let's look at some of the secondary grades, such as molybdenum. In this plot, it gets a little bit more complicated, and I would propose that this is a heterogeneous structure and should not be used in the actual modeling process. However, it gives us an opportunity to look at our data set and identify which of those data are the data that we don't understand. We can do some retrospective analysis and actually look at the data and try to build a better model. Likewise, if we look at both the silver and the gold, we even find more complications and evidence of maybe mixing populations. So this is a little bit of data analysis in terms of data mining and some ideas in terms of understanding what we're looking at for the quantitative resource assessment. Now, I'd like to share with you a little bit about economic resource analysis and some work I'm in the process of publishing. But in this case, the aim here is to translate estimates of these quantitative contained metals that are undiscovered into some meaningful societal measure. And in this case, there has been some application in the past that's been based on a U.S. Bureau of Mines empirical set of measurements, but the data the values are long dated, and so the equations don't hold for today's markets. So one of the things that we did here is we applied a hybrid modeling paradigm. In this case, we have a global set of data from approximately 380 mine sites, and we import that data, which disparate and sparse, disparate being many different kinds of variables with different that are not with the same units, but then with sparse matrix, maybe 20 to 30% is actually filled in terms of the matrix. And the other idea here is that our data is nonlinear. So we're interested in looking at relationships, so we evaluate the underlying multivariate density function for these relationships. And in fact, I won't go through all of this but in terms of showing you that, but there is a relationship. And we estimate the missing data, so the other data that are missing are imputed based on the underlying multivariate relationship. Once we have that done, we want to be able to check the bias, and we look at the bias and the uncertainty again in the modeling process. And we look for interesting cluster mergers based on k-means clustering and the Davis-Boydin criteria again. And on the upper right panel, you see that there's a number of different 14 economic resource units, which basically are clustered on statistics of the data that we have from the global. The second panel there in the middle shows an observed versus imputed data for just one of the factors, the variables we're interested in. And this is an economic variable that's distance to all-weather roads, which turns out to be important. You can see a nice one-to-one relationship. And then we take these data and we write the clusters, the median data, and in this case, there's lots of avenues to pursue, but in this case, I started with a simple approach of looking at multivariate linear modeling. So in terms of this regression process, I used the median cluster statistics and a best subsets analysis, and then I built and tested the models. An example is this, one of the models gives this panel on the lower right. You can see it says no and yes referring to whether it's economic. So in this case, we're just making this a binary indicator of whether the deposits are economic or not. So there's a pretty good relationship. On the left is the observed, and on the right is the predicted from our approach, using the empirical model derived using a hybrid approach. Now, if we take that up and apply that to a recent resource assessment the USGS did on a tract in British Columbia and the Yukon territories of Canada, we can find out that on the lower left panel there that 59.5% was economic and 40.5% was not economic. So this demonstrates just an application of that one particular model. And that brings me to the conclusion. What I found over the last couple of years in just some simple analysis is that computational intelligence provides an alternative paradigm that's worthwhile pursuing and at least considering in improving and providing insight for potentially helping us improve the USGS mineral resource assessment process. So thank you very much.
Thank you, Mike. My understanding is where the fifth speaker in this session has withdrawn. So what we might do is we may actually have question time for, say, the first four authors during that period, if that's okay. But if there's any immediate questions that you want to ask of Mike regarding any sort of clarification to the talk, could we have them now? Are there any questions? Okay. Our next speaker is Clayton Canara, and Clayton's going to talk on self-organising maps, a data mining tool for the analysis of geophysical data collected over the Brazilian Amazon. The co-authors are Canaro, Fraser, Costa, Silva, and Barros.
Okay. Good morning. My name is Clayton Canara. My presentation is titled Self-Organizing Maps, a Data Mining Tool for the Analysis of Airborne Geophysical Data Collected over the Brazilian Amazon. The research was developed in conjunction with universities from Brazil and CSIRO in Australia. The results form a part of my PhD studies that I finished last year. Most geological maps in the Brazilian Amazon are based on early airborne geophysical projects. Generally, these projects were completed in the 1970s. In 2004, airborne geophysical data collection was resumed in Brazil. With this, high-resolution magnetic and gamma-ray spectrometric data was acquired. New projects based on this technology enabled the review of the geological mapping process in the Amazon region. The Untitled project was developed in the Brazilian Amazonia, central western region of Pará. The big polygon here show the total area of the project region. However, we concentrate our studies in this small polygon. The principal reference for this area is the Xingu River here, and the Trans-Amazonica Highway that passes through the defined region study. The Untitled project was contracted by Geological Survey of Brazil, CPRM, and executed by Fugro Laza. For the project, magnetic and gamma-ray spectrometric data was acquired. The production lines were set in north-south direction, and the control line was setting in the east-west direction. The spacement of the production lines is 500 meters, and the control lines 10,000 meters. This picture shows the tectonic settings of South America in the Amazonas Craton. On the left, we can see in purple all the cratonic areas of South America. The biggest craton is located in the Amazon region. On the right, we can see the picture, and observe 7 blocks of crustal accretion. These blocks are covered by the Amazon basin in yellow. The study area is located in the Trans-Amazonas block, this block in green here. The geological setting is composed of very metamorphic granitic rocks such as Pacajá orthogonais in light pink. These rocks are in contact with mafic rocks of Três Palmeiras sequence in green. And Três Palmeiras sequence was mineralized in gold. Rio Bacajá metatonalite in dark purple. Bacajaí complex in light purple. And João Jorge intrusive suite in red are granitic rocks which are later intruded by these lithological units. Sometimes we have a big question in our life. We have many magnetic and gamma-ray spectrometric variables to consider in the Untitled project that can improve our geological mapping. But due to the amount of data processed, the big question was how to define the boundaries between lithologic units and identify geological process if these are reflecting characteristics of many variables. So a team met and discussed alternative methods to solve this question. Correlação was found to be a possible solution. It is a tool for analyzing and visualizing data in high-dimensional space based on vector quantization. The fundamentals of SOM. If we consider a multidimensional space that we are represented here, Each sample or pixel of each variable can be a vector in this space. If we consider all the pixels of the database as samples, we will have groups of samples which can be related to the variable's characteristics. In a multi-population sum dataset, some find the median vector of each population. The vector in color are samples, and the black vector are the sum node vector, or BMU. There are many ways to visualize the self-organizing map. This picture now shows U-matrix, which is one of the ways to visualize the self-organized map. In this situation, the dataset is represented by hexagonal nodes, that we can see here. The colors of the nodes, or BMUs, show similarities between different populations. Blue represents high similarity, and reds represent high dissimilarity. This picture shows the variables used in the analysis. We have 5 geophysical variables: the gamma ray variables, potassium, thorium, uranium, and total count. And we have also the magnetic variable, is analytic signal. As reference value, we stated in the table the statistics of each variable that we can see here. And then, to classify the variables' values, we used the median principle and classified it as low, medium, and high. Here we can see the contribution of each variable to self-organized map and the U-matrix. From this, we can observe some similar aspects, like the high contribution of potassium, thorium, and total count are coincident. Potassium, thorium, and total count. High dissimilarity in U-matrix is related to the high contribution of analytic signal and uranium. And you can see. This self-organized map was analyzed with K-means classification. The best number of clusters were determined using David and Bowen constant. The results showed 7 clusters to be the best number. Picture B shows the placement of these clusters in a self-organized map. This is the resulting spatial distribution of the clusters, which represent a pseudo-geologic map. In the next slide, I will talk about the characteristics of each cluster of this. Each cluster was related with the classification of the reference values from the original data that I showed in a table. Field sample was undertaken to check the geological characteristics of some clusters. A total of 89 outcrops were described, and the rock samples were collected for petrographic analysis. Cluster 1 is represented in orange and has low potassium, high uranium, and medium magnetic contribution. It was related to amphibolite rocks. Cluster 2, in blue, is composed for high potassium and medium values of other variables. It was related principally with leucomonzo granites. However, the principal gold occurrence in the area are related with this cluster. So you have an occurrence of gold here, and other here, and other here. All those occurrences are related with the cluster 2. Cluster 3, in red, is composed of medium and low values of gamma ray elements, contrasted by high magnetometric gradient showed by analytic signal. This is a common characteristic of mafic rocks. We found metagraboros and diabases as principal rocks in this cluster. We can see the principal direction of these clusters here and here to the diabase disks. Cluster 4 in green is composed of medium potassium and analytic signal, high thorium, uranium, and total count. In the field, we found laterites and metamorphic deformed zone related to this cluster. Cluster 5 in brown has medium potassium and analytic signal, high thorium, low uranium, and total count. It was related principally with metatonalites. Cluster 6 in pink is composed of high gamma ray elements and medial analytic signal. It was related with sienites. Cluster 7 in white has the same composition of cluster 6. However, in the spatial distribution, we found granodiorites and leucomonzogranites with diorites, as we can see in these pictures. So, as conclusion, the relationships obtained from the sound analysis can be used to improve geological mapping and to assist in the understanding the original of no mineral occurrence. Field work in an essential component to assist in understanding the sound response and to validate their interpretation. Sound has proven to be an effective tool to map various geophysical populations with similar characteristics on the airborne geophysical datasets. And both the magnetic and gamma-ray spectrometric data contain subtle relationships, which allows to detect and extract geological information. Correlation between the different geophysical data sets could be observed in the sound results. Thank you.
We are about 5 minutes ahead of time here, so do we have any questions to Clayton? Nothing at all? Okay. Thank you, Clayton. My apologies, I didn't introduce myself at the beginning. My name is Steve Fraser. I'm with CSIRO Earth Sciences and Resource Engineering in Australia. Okay, we'll just wait a couple of minutes for our next talk by Fabio Ibashati. The conveners for this session is Fabio Ibashati, Mike Friedel, Eduardo Vincent, and myself, Steve Fraser. Okay, there's probably a theme that you've seen. I'll try to ad-lib a little bit here. There's a theme that you would have seen through the first, at least, couple of talks, and it's to do with self-organising maps. And we've found, I suppose, as a group, that self-organising maps are quite an effective and powerful tool for the analysis of disparate and complex data sets. And it is actually quite a very valuable tool for that. It's a very powerful, robust tool. So we'll, that is the, one of the trends of this, this session. The technique was developed by a Finn, Tivu Kahunen, in the early 80s, and he actually developed it as a counter to neural nets. Neural nets were were becoming very popular at the time, and he actually developed the technique to counter neural nets, because most neural nets at the time were supervised, and he required an unsupervised technique to, for data analysis purposes. And hence, it's quite sort of it's quite a disappointment, I suppose, in some ways, that that technique is now actually classed as a neural net. And as Kahunen himself says, it carries all the burdens of the negative aspects of neural nets that were developed were being developed at the time. Okay, we've still got a couple of minutes. Mike, do you want to say anything? Yeah, well, we should wait till 11. So. Does anyone have any questions on anything so far? No? Okay. Okay, well, yes, okay. Well, Fabio. Introduce myself, please.
I'm not going to start the talking per se. I'm just going to introduce myself, talk a little bit about the work. Well, I'm Fabio Iwashita. I'm currently working with the Desert Research Institute. This work was developed while I was at Brazilian University, Campinas University, and I'm still finishing and completing this work at the DRI. So there is still a minute to go. Should I start? What do you think? Okay. Title is Soft Computing and Hydrogeological Characterization of Serra Geral Guarani Aquifer System, Paraná State, Brazil. The goal of this study is to build a hydrogeochemical spatial model for Serra Geral fractured aquifer, comparing with current conceptual models. We use the self-organizing maps method to determine nonlinear correlation between hydrochemical elements. Since these tables, they are incomplete, we have several missing elements in certain samples, so we imputate the missing values using the self-organizing maps. Then we applying the clustering technique, the k-means, to find relevant clusters and classifying them. This way, we expect to survey possible fluxes and connections, hydraulic connections between Serra Geral and aquifer system. So a little bit about the Guarani Aquifer. The Guarani Aquifer is the largest aquifer in the world. It's intensely studied. It's composed by eolic sand deposits, and it covers 4 countries: Brazil, Paraguay, Uruguay, and Argentina. And the Serra Geral Aquifer, the Guarani Aquifer, it's covered by a basalt leakage, the Serra Geral Formation, that also constitutes an aquifer, but it's a fractured aquifer composed of this sequence of leakages, and can be as thick as 1.6 kilometers, can be 1 mile thick. And it's also one of the largest leakage. Basalt leakage extends to most of the area of Guarani Aquifer, and it also has a portion in Africa. the same leakage sequence of leakages. More specifically, our study focused on the Paraná state. We have here the Paraná state outlining the boundaries in red, and the Serra Geral, going to be focused on the Serra Geral formation marked by this V's area. You can see the outcrops of the Guarani Aquifer in dark red, or more like brown. Okay. And it's also, the Serra Geral covers 4 countries. Let's see, just a second. Oh, yeah. It's kind of hard to see, I'm sorry about that. But you have here a close-up on the region with the fractures and the rivers and 900, almost 1,000 points of sampling. The current conceptual model about the connectivity between these two systems states that the hydraulic connectivity is mainly driven by the fracture that crosses both systems. So you have both upward and downward fluxes connecting these two aquifers. So the Serra Geral aquifer system is the typical signature is basically calcic and magnesium with also a high concentration of bicarbonate. While the Guarani Aquifer system is the typical elements are sodium, chloride, sulfate, and fluoride, also bicarbonate. They're typical to both aquifers. Also, recently, there have been studies of the influence of surface characteristics that would have over the chemistry in the groundwater. In this case here, we have another conceptual model showing 2 different conditions. We have condition 1, where you have a thick layer of soil that would slow down the infiltration of water. And the soil there can be as thick as 50 meters thick, very developed soil. In this, on the same situation, we have a lower density of fracture. This way, the upward flux will be, you will have more favorable conditions to upward fluxes. Thus, the water found on the Serra Geral aquifer will have higher content of sodium, and sulfate, and fluoride on these waters. And in this condition too, the thickness of the layer, of soil layer, will be smaller, and we'll have a more dense network of fractures. And this way, the recharge from precipitation will be higher, and this way the elements will be more typical to Serra Geral than Guarani. So the basic idea behind this work is to all the samples, all the wells are from Serra Geral aquifer system, and if we find anomalous chemistry on these waters, that would indicate a potential connection between the Guarani and the Serra Geral, would indicate an upward flux from the Guarani. Oh. The self-organizing map, can be considered an unsupervised artificial neural network or a quantized vector, where for each sample we assign a vector. And this vector is it's an n-dimensional space where n's the number of variables. And this sample, they are iteratively rearranged, where they are gathered by Euclidean proximity, by similarity, while the aim is to preserve the topology, the neighborhood of the samples, and this way preserving the correlation between these variables. The samples are projected on a component plane, and this map is projected on a toroid. That is a topological figure. It's this donut here. And the nice thing about the toroid is that when you unwrap this figure, you have a rectangle where the edges are connected. And this way, problems that we have usually with classification methods, the border problems with the classification methods, they are diminished. We get better results. And this last figure is just another illustration of how the representing how the vectors work. You have similar colors to similar samples in the space, in the high-dimensional space. And you have a representation of the unified matrix on the right. This is the procedure that we followed to achieve our goal. We had two different data sets, a hydrochemical data set and pump test data from a way smaller data set that we use to calculate using a MATLAB script to calculate transmissivity based on calculated from specific capacity values. These two data sets, they were processed through the self-organizing maps, where we obtain the correlation matrix, the self-organizing map, and then the self-organizing map model, and then we inputtate the values, and then we obtain the estimated data for the table. We complete a table that was we had several missing values on the table because they came from different agencies, the analysis. And they were scattered in 5 years. In the midterm, they decided to include more elements to the analysis procedures. Finally, we applied the K-means clustering to classify this data, and then we obtained the hydrochemical and the transmissivity surfaces. So the component planes, they can be thought as a two-dimensional histogram, where in this case here, we see like a reddish color would indicate higher values of the variable, and bluish colors here will have the more lower values of the variable. And when we have similar colors and similar positions on these component planes, it would indicate a correlation between the variables. Like we have here with the, is this a laser pointer? Oh, that's good. We have here calcium and magnesium. They have like a closed configuration, indicating a higher correlation between these two variables. The unified matrix summarize the dissimilarity between the nodes, which will be each unit of these maps. And the K-means clustering technique is calculated over this U matrix that summarize the similarity. I'm going to just show a couple of maps given the limit of time. These are the results for calcium, which is a typical element of the Serra Geral aquifer system. In the light blue colors here, we have the samples where we actually have the measure for calcium, while the dark dots here, the black dots, are where we have missing values for these wells. So we have here the fractures. Here, this region here is, we have a system called the Ponta Grossa Arch, where we have its big lineaments here, and supposed to have a high connection between the two aquifers. Let's see. So we have high values over here, and just would like to point out that we have low values for calcium here and here. Bicarbonate, since it's typical for both aquifers, will be more tricky to evaluate, but we have high values here, the same region here. Oops. Total dissolved solids, oh, I forgot to mention, sorry. We had a total 37 variables, including hydraulic properties and hydrochemical properties, plus some geophysical measurements like aeromagnetic measurements that would reflect more deeper features of the aquifer, and the hydrochemical variables. And the total dissolved solids, it reflects the time of residence, might reflect the time of residence of these waters in the aquifer. So we have here actually the model is forecasting higher values of total dissolved solids without any sample actually measured there. And here we have the fluoride content, which will be a typical signature for the Guarani Aquifer. And we have, the samples are concentrated here, and all this region is estimated. The interesting thing about this result is that this region here, previous studies have already shown that you have higher values of fluoride in the rivers and groundwater close to the surface. And this is, they are high, the contents are so high that they are causing health problems like both teeth problems and liver problems given the content of fluoride. And this map summarized after the K-means clustering classification, it summarized the map that we obtained showing the typical waters for Serra Geral or recent recharge waters, transition areas where would we will have both signatures between, both for Serra Geral and Guarani Aquifer, and what will be more typical for Guarani Aquifer on this region over here. And it also agrees with the previous studies where the connection will be more driven by structures, and others also studies that were investigating these connections between the aquifers. So, in this work, we investigated hydrochemistry and groundwater physical properties based on incomplete tables where we imputed the values. Then we revealed this and quantified these nonlinear relationships based on the huge and large set of variables. And most important, that will not be possible using parametric approach, multivariate linear analysis, because the table is incomplete. This way, we coped with incomplete information from Wells database, and we think that will be a good asset for when conceiving numerical simulations for numerical modeling, both for fracture medias and porous media. That could be used as part of the zonation process, or part of the, could be used as initial condition for the numerical simulation. And that's it. Okay.
Fabio, you've come in well in front of time. Is there anything you want to clarify?
Well, I have a couple of additional maps here for that was like hidden for in case of the kind of couple of slides here hidden in case of questions show up. I have here the equation that was used to calculate the transmissivity using the MATLAB script, the set of variables, the units for these variables. We have some GIS derived variables as well that would reflect, that might reflect the lineaments and the geophysical. Oh, I have some maps here that I couldn't given the shortage of time for sulfate that also will be typical for the Guarani Aquifer. Sodium, same case. Guarani Aquifer. And some explanation about the possible origins of sodium and the sulfate. Nitrate and chloride, this was kind of interesting because chloride is a conservative element that could use as a tracer element on numerical simulations, and nitrate is not typical, it's anomalous for both aquifers. This way, it would indicate a contamination, possible contamination by human activities. Interesting thing here is that shown high values over here, and these two clusters of points here, they are actually two big cities, and the place where the self-organizing map predicted the high content of nitrate in groundwater is where actually this city, they discharge the sewage. Even after the treatment, you have high content of nitrate, of course. And Oh, and some nonlinear correlation, because this is one of the advantages of the self-organizing map. It calculates the correlation table even though you have an incomplete table. Yeah, that's what I have additionally to show. Any question? Okay.
With regards to your maps that you produce, have you looked at that in terms of the hydraulics and the flow system, in terms of directional flow using a potentiometric curve?
Repeat the question.
Okay. So he asked if I have used the same maps to use the general flow, the regional flow of the hydraulic properties, like the general flow in the basin, based on the potentiometric levels of these maps. And yes, I have investigated the just in a I'm in an early stage of investigating that, but we have the potentiometric levels estimated by some, and then we can calculate the general direction of these flows in a fractured aquifer. Most studies are of these two aquifers. They are mostly done on the Guarani Aquifer because it's a porous media aquifer, and it's very important because you have way higher yield when pumping. So cities, they would drill a well 2,000 meters deep to extract like 1,000 cubic meters per hour to supply a city, while the Serra Geral are mostly used for small communities and villages and farms. But it's also really important, but it's less studied.
One other question. What are you planning to do as an extension to this work?
Repeat the question.
While I'm planning to do as extension of this work, now the next step will be the numerical simulation itself. So we can actually predict how and calculate the uncertainties of, the numerical simulation, and calculate the uncertainties of this model, which will be the most important step. And that's it. So I'm going to get the queue and call the next speaker. Next speaker is Eduardo Vicente. It's a landscape discrimination in Brazil using Hyperion data and self-organizing maps approach.
Morning, everyone. This work was so important to me because besides the important collaboration among USGS and DRI, I have an opportunity to work with my friend Michael and Fabio. So we have here, sorry. Okay. The main goal of this work was evaluate nonlinear approach, specifically SOM, self-organizing mapping, to classification of complex and massive data set in remote sensing. When we think about the massive and complex data set, we think in both ways. The first way is a tropical environment. It's so different, the tropical environment, when we think about the high heterogeneity of targets, high variation in soil characteristics, color, texture, etc., a massive presence of vegetation. Here in semi-arid climate, we have vegetation such as a background, because the vegetation is so different. We have in the tropical environment higher biodiversity, and the vegetation wasn't properly background, but important part of the game. The massive presence of the organic matter is a problem too, because we have a lot of moisture in the soil. Think about that characteristics. We took a study area in Minas Gerais state, and with Hyperion dataset. Hyperion was launched in 1999. So until now, Hyperion is an important hyperspectral sensor and works with the experimental hyperspectral sensor. And until now, it's only is a unique orbital sensor work now. When we think about the hyperspectral remote sensing, we talk about the contiguity bands, and at 100 bands. Comparatively, when we take the Aster comparatively and the ETM, here we have 6 and 9 bands. Hyperion, like Averys, for instance, and another hyperspectral sensor, has, in the case of the Hyperion, 220 bands. Here we have a hyperspectral data cube. Is a good example about the same area. We have radiation, electromagnetic radiation, split in several pieces, or whatever. We have entire information about the spectral signature. In this example, we have a soil and vegetation. Each one of these shoulders, the difference between shoulders and the lower area, we used to call spectral signature, because we have different measures around, over the targets on the surface. So, it will be a paradise if Hyperion wasn't a complicated hyperspectral sensor, because we can call Hyperion such a first-generation orbital hyperspectral sensor, or whatever. So we have a lot of noise when we compare ETM with the Hyperion here, spectral signature. In the white circle, we have a lot of noise. And the peculiarity of the noise is a non-linear noise. So when we have an entire spectral library characteristic here, when we convert that information to Hyperion, we lost a massive information. Traditionally, we treat that kind of information of Hyperion with linear model approach. And in this work, we try a non-linear approach. It's a new perspective over the Hyperion. Dataset, another problem involving Hyperion is dataset size. 10 megabytes is the minimum. When I start work with Hyperion, this size tends to increase during the processing. And signal to noise is under 100 to 1. Mike used to call the Hyperion dataset the King Kong, because it's very hard to processing that kind of data. In the pre-processing stage, we used to call bad bands, water vapor absorption bands, and the overlapping bands is a genetical problem of a Hyperion, and convert to radiance, this kind of data, to reflectance. Why reflectance? Reflectance is a straight comparative measure with another spectral library available, for instance, in the labs or in the internet. This kind of measure is important to a comparative processing procedures as follow. Here, I don't expend much time explain the SOM procedures because my colleagues explained very well before. But the main objective here, the goal here is idea the generation new data from clusters, identify unusual relationships into the data set, it reduces the dimensionality of the data set and preserve the topological relationship. So, in resume, we destroyed the spatial relationship and conserve the topological relationship. From to Hyperion or remote sensing, it's so important because a geostatistical approach used to maintain, keep the spatial relationship is, in most works about this approach, show that is not so efficient. Here we have a strong, powerful visualization of the SOM results with the colors, with clusters, colors, cool colors with similarity, and hot colors means dissimilarity. And the strategy of processing of SOM in this figure, I can explain one thing here. This most important thing here is a genius trick, because we have 12 by Fabio and then the Michael, because we had 12 spectral features, spectral library curves. For the hyperspectral image is not enough. It's a problematic input. So the 12 curves was simulated with noise and multiplied for 2,000 spectral curves. That 2,000 spectral curve was applied to self-organizing map. After that, applied to hyperspectral imaging of Hyperion. And after this, Hyperion was classified. So it was important because if I work with Michael and Fabio, try work only 12 curves. It wasn't a good result. Or whatever. Good strategy. That 12 curves I show here. In resume, I have the soil spectral features and vegetation spectral features that I put here and multiply to here. So here I have several characteristics of soils and probability they exist in the area. With soils with high reflectance means sand soil, low reflectance means iron oxide abundance, clay minerals. All the information was considered in the SOM procedures. Here I have since forest with the greenness, higher greenness, until dry grass. That characteristics was considered in the SOM procedure here. So here in this picture we have 3 groups. That 3 groups in the unified matrix means exactly this: vegetation, oxide soil, and bar soil. So SOM can attempt and isolate vegetation, oxide soil, and bar soil. And without a lot of strong information about this area. Another result, a good result, when I put together that fractions of the image, I have a transitional areas over the area. The result show the low abundance of vegetation, high abundance of vegetation, and subsequently oxide soil and bar soil. And when I put together, I have transitional areas. So if I have cut off the bar soil and work with only vegetation, I can. And to another fraction. Here, I have an overview, visual overview, and the bar soil is not a hard, is not an easy processing, identify oxide soil. And here I have vegetation around and the oxide soil in this area, in the yellow circle. And here, on the right, I have Hyperion, color composite, original. I have red associated to soil, but it's not be clear in the original data set. And here I have the information much more clear. Here in this picture, comparatively, I have vegetation well defined here and here, here. Yeah, I have vegetation here is associated green pixels. Here I have bar soil area 2. But only the visual checking is not enough to us, and we're checking with the spectral library comparatively with the Hyperion classify image. So the results show higher values in the R. I have here spectral library and the bar soil classification, more 2 comparative control targets. Here I have oxide soil comparatively with the hyperspectral Hyperion classified image with good results too, reasonable results. Here I have one more. Here is my deception, because the initial hypothesis was try separate grass or pasture, because degraded pastures is so important to carbon balance, and the misclassification with the bar soil is so higher. In this empty, and is our at this moment we can't separate it, pasture and bar soil, mainly due to OH molecule bonds, because both vegetation and bar soil have this kind of bond molecule. So we'll be trying again. Here we have a validation with vegetation and final conclusions. Despite the non-removal of riparian original noise, the SON approach was able to several spectral characteristics of the targets. And traditionally, when we will work with the Hyperion dataset, we applied geostatistical or traditional statistical remove noise method. In this case, SON was completely responsible of that results. The use of spectral libraries as a feature on the SON process was extremely efficient. This approach allows a semi-quantitative mapping using SON. We have a range between 0 and 1. So, such a fuzzy approach, we have a transitional values that one of each that fraction. And interesting thing here, we don't need take a spectral radiometer and take measures on the field just for validation. Here, we use a generical spectral library. Take the internet or in my personal data set. So The idea is applied the isonomic spectral library to another Hyperion datasets in other areas. It's much easier. Pasture and bare soil showed the higher spectral ambiguity among all the targets under the investigation, probably due to the presence of the, I talked about this before. And the SON was able to map areas with iron oxide soils. This is not a simple task, because when I have oxide soil, the possibility to confusion with the low albedo areas, low energy areas, such as moisture soils, or whatever, huge vegetation, large areas of shadows, for instance, the possibility increase. In this case, we don't need extract the shadow fraction from image, and even that we can identify. We know about the presence of oxide soil, but we don't know where exactly. And we until the SON approach, we don't have how validation. Okay. Thank you very much.
Thank you, Eduardo. Do we have any questions? I mean, it'd be great if we created some sort of discussion at this point. Our next talker hasn't shown, and so we do have an opportunity here to engage in some discussion. Would the speakers from this morning like to come up on the stage, or just at least become available, and maybe we can have a bit of a talk. Would anyone from the audience, those of you who are left, have any contribution in terms of computational techniques for data analysis? And you might want to mention how you access or undertake the analysis of large data sets, because this is what this whole session is about. Finding efficient methods to do that. I do have a question for you. I'm sorry. That's okay. Using SOM to compute such a large data set as Hyperion, that must be a massive exercise computationally. Have you had to go? How have you addressed that? Because that must be not an easy exercise.
Yes, I agree. But if you think about the, I took only 12 spectral figures, and I work with only 12 spectral figures, and multiply, open a new possibility to reduce the processing time. I understand Michael tell me how much time the computer spent to process Hyperion or another image. You tell me, you spoke about this problem in Campinas too, but I see that kind of approach, a possibility to reduce that time, and we've been thinking about another methods, linear approaches. The time in processing and the results is not so good too, and you spend less time, but the results need adjust. Some provide a good result in a first shot, I believe, and the initial step, but I like very much.
Michael. The question is, has Eduardo thought about how to extend the approach he's taken with the Hyperion data to some sort of hybrid approach, which presumably is using both computational methods and other techniques.
Could you repeat the question? I lost.
The question is, one is, you work with soft computing, the software. Is there a way to go to another level, perhaps, to provide some empirical equations? So could you go to the hybrid step and use some traditional approaches and build predictive equations, for example?
If I understood that question, I believe that idea was one of the first idea that we have. I believe, if I remember, because the predictive methods is one of the goal that take the Hyperion dataset or a massive complex dataset from another hyperspectral sensor and put another methods together. In my opinion, is a very good strategy. I'm optimist, but that result is not an easy result. Was not a easy result. You know that. And if you put hybrid strategy, I think you can achieve results, very well results. I ask your question.
Okay. Do we have any further questions? Okay. The next talk is due to start at 12 o'clock. So could we please be back and ready just a few minutes before 12, so we could have the final session for this, the final talk for this session. Thank you.